Welcome to Factopia, where hidden facts come alive. Today we're diving into one of the most fascinating and powerful metals in the world, titanium. You see it in airplanes, spacecraft, medical implants, and even high-performance sports gear. But how is this metal actually made? How do we turn rocks from the ground into one of the strongest and lightest metals known to humanity? Let's uncover the incredible story of titanium, step by step. Titanium is a remarkable element. It is represented by the symbol T on the periodic table and has the atomic number 22. One of its most amazing qualities is its unique combination of strength and lightness. Titanium is almost as strong as steel, yet it weighs about 45% less. This makes it ideal for applications where strength-to-weight ratio is critical, such as in aerospace, sports equipment, and medical devices. The metal is also highly resistant to corrosion, even in salt water, chlorine, and acidic environments. That's why titanium is often used in marine equipment, chemical plants, and surgical implants, where both durability and biocompatibility are essential. In fact, titanium is completely safe for the human body, which is why you'll find it in hip replacements, dental implants, and even pacemakers. Despite all these amazing properties, titanium is not something you can easily find in its pure metallic form in nature. Unlike gold, copper, or iron, titanium is never found as a free metal in the Earth's crust. It is always combined with other elements to form ores, most commonly rutile and ilmenite. These ores are abundant and distributed across the world, with major deposits found in countries like Australia, South Africa, Canada, and Norway. Titanium was discovered in 1791 by a British clergyman and amateur mineralogist named William Gregor. He found a dark, heavy sand in a river in Cornwall, England, and noticed it contained a new metal oxide. Around the same time, a German chemist named Martin Heinrich Klaproth independently discovered titanium in the mineral rutile and named it after the Titans of Greek mythology, due to its strength. For nearly a century, titanium remained a scientific curiosity. Chemists struggled to isolate the pure metal because it reacts so readily with oxygen, nitrogen, and other gases when heated. In fact, early attempts to smelt titanium failed, because ordinary furnaces could not reach the required temperatures or control the chemical reactions properly. It wasn't until the 20th century that titanium production became industrial-scale feasible. The metal's remarkable properties made it highly desirable for aerospace applications, especially during World War II and later during the space race. The development of the Hunter process in the 1920s and the Kroll process in the 1940s finally allowed titanium to be produced in pure, metallic form. These processes remain the foundation of titanium production today. Titanium is abundant in the Earth's crust, making up about 0.6% of it. But it is almost always found in combination with other elements. The two main ores are rutile and ilmenite. Rutile, a naturally occurring mineral that is about 95 to 97% titanium dioxide. Rutile has a reddish-brown color and is highly valued for producing pure titanium. Ilmenite, a black iron titanium oxide mineral, which is less pure than rutile, but more abundant worldwide. Once mined, these ores are crushed and purified to extract titanium dioxide. This step is crucial because titanium is highly reactive and must be isolated from oxygen and other impurities, before it can be reduced to metal. In many cases, titanium dioxide is also used in pigments for paints, coatings, plastics, and even sunscreen, so it has multiple applications before becoming metallic titanium. Global titanium production is concentrated in countries with large reserves of these ores. For example, Australia produces the majority of rutile, while South Africa and Canada have significant ilmenite reserves. The ores are transported to processing plants, where they undergo a complex chemical transformation to become titanium metal. Now comes the most fascinating part: how titanium is actually made. Titanium production is not like smelting iron in a furnace. Titanium is extremely reactive at high temperatures and will combine with oxygen or nitrogen to form compounds, making it brittle. To produce metallic titanium, chemists use a two-step industrial process. Step 1. Conversion to titanium tetrachloride. The first step involves converting titanium dioxide into titanium tetrachloride, a liquid compound. This is done by reacting the purified titanium dioxide with chlorine gas in the presence of carbon at temperatures around 900 degrees Celsius. The titanium tetrachloride is a volatile liquid that is highly reactive but much easier to handle than solid titanium dioxide. It's sometimes called tickle by industrial chemists. This liquid is then purified by distillation to remove impurities, preparing it for the next step. Step 2. Reduction to titanium metal. The purified titanium tetrachloride is reduced to metallic titanium using the Kroll process, which is still the most common method today. In this process, titanium tetrachloride is mixed with magnesium megagram. In an inert atmosphere at around 800–900 degrees Celsius, this produces a porous form of titanium called a titanium sponge. The magnesium chloride byproduct is removed and the sponge is cleaned thoroughly. Alternative process? The Hunter process. Before the Kroll process, the Hunter process was used, which reduces titanium tetrachloride using sodium instead of magnesium. While it's less common today, the Hunter process laid the groundwork for modern titanium production. Step 3. Purification and shaping. Once the titanium sponge is obtained, it is melted in a vacuum arc furnace to remove residual impurities. The molten titanium is then cast into ingots, slabs, or billets. These can be further processed into sheets, rods, wires, or complex shapes for industrial and commercial use. It's important to note that all of these steps require extreme precision, high temperatures, and controlled environments. Titanium can't be smelted like iron or aluminum because it reacts violently with air and other elements, which is why it's never made at home. The production of titanium may be complex, but its applications are truly extraordinary. Titanium's combination of lightweight, strength, and corrosion resistance makes it invaluable across many industries. Aerospace and aviation. One of the largest users of titanium is the aerospace industry. Airplanes like the Boeing 787 and military jets use titanium in engine components, landing gears, and airframes. Titanium's lightweight property reduces fuel consumption while maintaining strength and safety. Medical implants. Titanium is biocompatible, meaning it doesn't react with the human body. This makes it ideal for hip replacements, dental implants, and surgical screws. Surgeons prefer titanium because it's strong, durable, and safe for long-term implantation. Industrial and consumer products. Titanium is used in chemical plants, desalination plants, and marine equipment because of its resistance to corrosion. In the consumer market, titanium appears in watches, high-end bicycles, sports equipment, and eyeglass frames. Space exploration. Even NASA relies heavily on titanium. Rockets, satellites, and space shuttles use titanium components to withstand extreme temperatures and high stresses. Its ability to remain stable in harsh environments is unmatched by other metals. In short, titanium's unique combination of properties makes it essential for modern technology, healthcare, and industry. It's crucial to emphasize that making titanium is extremely dangerous. The industrial process involves high temperatures, molten metals, and toxic chemicals like chlorine gas. Any attempt to reproduce this at home could be catastrophic. All production occurs in specialized facilities with trained engineers, protective equipment, and strict safety protocols. Titanium is safe once it's purified and shaped into final products, but the manufacturing process itself is highly hazardous. So if you've ever wondered if you could make titanium at home, the answer is absolutely not. Stick to learning about it, exploring its properties, and appreciating the science behind it safely. Before we wrap up, here are some amazing fun facts about titanium. Titanium is as strong as steel, but 45% lighter, which is why aerospace engineers love it. Titanium can withstand temperatures over 1,600 degrees Celsius, making it ideal for jet engines. The metal is biocompatible, meaning it won't corrode or react inside the human body. Titanium dioxide, a derivative of titanium, is used in sunscreens, paints, and even food coloring. Some of the world's most expensive bicycles and watches are made from titanium because it's light, strong, and stylish. Titanium is truly a hidden hero in our everyday lives, even if most of us never see the raw metal. And that is the incredible story of how titanium is made, from rock in the ground to the strong, lightweight metal that shapes our world. If you enjoyed this deep dive into the science and industry behind titanium, Make sure to like this video, subscribe to Factopia, and hit the bell so you never miss an unseen fact. Factopia, where hidden facts come alive.